The lesson for geometry and spatial sense is called the Wheel of Theodorus, and if you haven't heard of this term before, then you're in for a real treat. But first we're going to begin by looking at this equation right here, which many of you will recognize as the formula for the Pythagorean relationship. We all learned this formula in middle school or high school, but many of us, while learning it, did not actually encounter the concepts upon which it is based. This is really too bad because there is a lot of surprising and aesthetically pleasing math behind this formula. In this learning experience, the formula comes toward the end. We begin by having students investigate right triangles. First, we get them, either on geo boards or dot paper, to create a right triangle. Then we get them to create the squares on all three sides of the triangle. So if this is side A, what does A squared look like? If this is side B, what does B squared look like? If this is side C, what does C squared look like? Then we get students to determine the areas of the squares, and we come up with something that looks like this. Now, they can see that the areas of the squares, the areas of the two smaller squares together equal the area of the larger square on the hypotenuse. In other words, A squared plus B squared equals C squared. It is essential that students experience this multiple times to see that this relationship is consistent. Once they understand the relationship, they can develop a formula. Too often, I think, teachers lead with the formula and assume that students will just get the concepts, but in truth, many students will not, and it shows when they have difficulty using the Pythagorean relationship in any way that is not a straightforward substitution of values for A and B to determine the hypotenuse. If they have this surprising aesthetic experience, then they have something solid in their minds that can ground the formula. Then they'll be more likely to understand it completely and retain it for life. So that's what's happening in the first part of the lesson. I'll say a little bit more about what happens in the coding aspect of the Pythagorean relationship in the next video. In part 2 of this lesson, we will move on to a consideration of the Wheel of Theodorus. This is what it looks like. It starts off with this triangle here. It has a base of 1 unit and a height of 1 unit. And if you do the math, you will see that the hypotenuse, the length of the hypotenuse, is the square root of 2. Now, it's interesting to see how this design progresses. The hypotenuse of the first triangle becomes the base of the second triangle, which still has a height of 1 unit and still has a 90-degree angle. This is going to create a longer hypotenuse, which becomes the base of the next triangle. If we take a more detailed look at the wheel, this is what we have. Of course, we see a lot of really interesting math here. Determining the lengths of these hypotenuses requires the students to use their knowledge of the Pythagorean relationship that they will have acquired in the first part of the lesson. It is quite an interesting discovery to see that the hypotenuses follow the pattern in that they are square roots of consecutive integers. Now, most of these hypotenuses are irrational numbers, so this learning experience provides a nice segue to an investigation of the nature of rational and irrational numbers. The Wheel of Theodorus has a few other interesting mathematical aspects to it. It is said that if you build a rectangle around it, the rectangle would have golden proportions. In addition, it is also said that if you continue past the 17th hypotenuse here and keep on making triangles so that they overlap, no two hypotenuses will ever overlap each other. Another interesting thing about this is if you take these 1 unit sides, these ones right here, each one is 1 unit long, and extend them, they will never intersect with any of the existing vertices in the feature. So there is a lot of very interesting geometry at play here. Once students work on this through the lens of the Pythagorean relationship, the stage is set for rich mathematical investigation.